Hello, and welcome to EBL class from the Marvell Nanofabrication Laboratory at UC Berkeley. This class will introduce you to electron beam lithography. We will cover how electrons expose the various resists used in electron beam lithography, proximity effect and how to correct for it, as well as some basic tool operation. Let's begin by zooming out to see the big picture. What are we trying to accomplish with lithography? We are trying to create a pattern in an otherwise unpatterned film or substrate. This can be done by etching into an already existing film or by lifting off a film onto an underlying resist layer. The exposure tools we use to create these patterns either use photons or electrons. So, why would you choose electrons over photons? Resolution. The smallest feature you can routinely achieve on a chip using our photolithography tools is 600 nanometers on our MLA150 tool. The smallest feature you can routinely achieve on a wafer is 200 nanometers using the ASML stepper. If you need to resolve features that are smaller than these sizes, you will need to use electrons for the exposure. And we'll talk about why electrons and photons work like this more in a moment. Why wouldn't you choose electrons over photons? There are two main reasons. One reason is that electron beam lithography often is a bit more complex than photolithography. But the main reason is throughput. Throughput refers to how long it takes for the pattern to be exposed. One of the consequences of having high resolution is that the write time is longer, often significantly longer. There are, of course, exceptions to these general rules. If you are unsure of whether you should be using electron beam lithography, please reach out to process staff to discuss your specific application. Let's spend just a few minutes talking about throughput. In a university setting, this is not often a concern. We don't care about the number of wafers produced by hour. But in the case of electron beam lithography, you can absolutely come across a pattern, a settings choice, a design of such complexity that it would take days to expose, which is untenable in a shared use facility. Why does it take so long to expose using electron beam lithography? Well, let's look at how an electron beam exposure works. We start with a focused beam of electrons being emitted from a source that is directed to different sites across the sample. However, that beam of electrons can only be deflected so far, usually on the order of about 1 millimeter. So your pattern needs to be divided into smaller chunks. These are called fields. The stage will move so that the beam is centered on a single field. The beam will deflect across that field, and then the stage will move to the next field. These fields can be divided into subfields, although this is not true on the NanoLab's Crestec tools. If working on a tool with subfields, the tool has two deflection systems, one which deflects the beam to the center of a subfield, and a second deflection system that deflects the beam within that subfield. In either case, fields and subfields are themselves divided up into individual shots. In the image here, we see a sample which is divided into 16 fields, with the shots being exposed by the deflecting beam for the field below the emitter. Earlier, I mentioned that the resolution of a photon and an electron are quite different, so let's take a moment to discuss this further. For photons, you can approximate the resolution by using the Rayleigh criterion. R equals 0.61 times the wavelength lambda, divided by the numerical aperture NA of the tool. This criteria was designed for microscopes, and it is truthfully a vast oversimplification for lithography systems, but it is the starting point to understand resolution. We know the photon wavelength and numerical apertures for our systems, giving the Rayleigh criterion values shown in the table below. Actually able to achieve better resolution than the Rayleigh criterion values suggest. On the MLA150 system, we can achieve 600 to 700 nanometer features. And on our ASML tool, we can actually get sub 200 nanometer features, which is often a typical size for EBL applications. The issue is that ASML is a wafer scale system. For researchers who are working on chips, it is usually incompatible with those samples. This brings us back to the resolution limit for electrons. Using quantum mechanics, we can calculate the wavelength of an electron based on its accelerating voltage, making sure to account for the relativistic speeds of the electron. When we plug these electron wavelengths into the Rayleigh criterion, we get theoretical resolution values which are substantially smaller than what we can actually achieve on the tool. On our 50 kV system, our best resolution is 10 nanometers. In our 100 kV system, our best resolution is 7 nanometers. Why is there such a difference between the theoretical resolution and the actual resolution? There are two reasons for this resolution limit. The first reason is that electrons have a property that photons do not. They have a non-zero charge. Electrons repel each other. While an individual electron has a minuscule wavelength, a beam of electrons has a real physical size. When we are working at the scale of nanometers, the physical size of the beam will directly affect the size of the features we are able to write. Additionally, we also need to account for the non-zero size of the resist molecules themselves. At these length scales, some amount of the resolution limitation is also due to the length of the resist polymer chain itself. So you've done your due diligence, and electron beam lithography is the right exposure technique for your device. Now it's time to plan your process. Here we see a comprehensive chart showing all the different pieces that contribute to an EBL process. This graphic was originally made by staff at the University of Washington. This is my own modified version. In this chart, we have three main components for EBL processing: planning, the EB write, and follow-up. Which of the three components takes up the most space? Planning. When you're done with EBL class, I want you to walk away knowing that you have to do some prep work before you can sit down and just write a device. But once you have a working process and you've done that calibration, you should have a process that works across different designs and even possibly with different films and substrates. So in this next section, we're going to talk about the different pieces you need to account for when planning your EBL process. We'll start by walking through the details of how resist is actually exposed, which will then lead to the different EBL resists and why you might choose one versus another. We're then going to talk about the proximity effect, and finally, we're going to talk about job file preparation for our Crestech EBL tools. Let's consider exposing just a simple one-dimensional feature. In this example, circles represent pixels that make up the feature. Black circles represent the beam being blanked and no exposure is occurring. White circles represent that the beam is on. If we think of this now in terms of energy input, we have zero energy input in the unexposed regions, and then some energy EI in the exposed regions. Ideally, this is a step function going from the unexposed region to the exposed region. However, since the beam itself has a finite size and shape, a truer representation of the energy input will have some slope at the edges of the feature. Additionally, there is some minimum threshold below which the resist is not converted into its exposed product. Labeling this as a threshold is a bit of a simplification and doesn't take resist contrast into consideration. But this model will work for now. This threshold value will turn out to be the resist sensitivity, which will be discussed in greater detail later. So what happens as we increase the energy dose to this feature? Initially nothing, as we are below the minimum threshold required to convert the resist. Once we meet the threshold, the exposed resist will start to react with the developer. For positive resists, this area will be washed away. For negative resists, this area will remain. And what happens as we increase the energy past the threshold? We can best understand the impact of higher energy by looking at three different doses: low, medium, and high. On the left and right sides of each graph, there are no electrons being sent into the system, and the resist remains unchanged. At the center of each graph is the exposed region. This is the same width for all three doses as indicated by the dashed black lines. The transition zone is where there is a substantial difference. When more energy is put into the system, the intercept point changes for each curve. The resulting feature gets wider and wider with increasing dose. We can turn that effective width, which is the line width of the desired feature, into a plot, where the width of the feature is on the y-axis and the dose is on the x-axis. If we compare this with real data, see that this model does appear to correlate with a real measurement. Great, so we're done, right? Unfortunately, it's frequently not that simple. We're going to take a closer look at some of the SEM images from the dataset we're using here. When we analyze these images, we will be looking for 3 different factors. Are we getting our desired feature width? Is the line edge roughness smooth, i.e. low, or rough, that is high? And lastly, if the dose changes, what impact does that change have on feature size, which is a measure of the process variability? The patterns here are 200 nanometer spaces and 200 nanometer trenches. The feature we are measuring is the exposed feature, the trench. In this first image, the mean trench width is 193.8 nanometers, which is 6.2 nanometers smaller than the target size. However, the line edge roughness is unacceptably high, and we'll see that the process variability is too high as well. Looking at the next dose we tested, the trenches are now oversized at 217.6 nanometers. And while the line edge roughness is better than before, the line edge is still not particularly smooth. Now we can get a sense of the process variability. The dose increased by 20 microcoulombs per centimeter squared. The feature size increased by more than 20 nanometers. And if we had decreased the dose by 20 microcoulombs per centimeter squared, which I'm not showing in this video, the features don't resolve at all. This is because we're in the knee of the line width curve, where a small change in energy makes a big difference in the line width. So what should we do? Well, let's look at an image at a higher energy. At higher energies, there is still an increase in feature size with an increase in dose, but it's linear instead of nonlinear, which is more controllable than the large nonlinear increase we see closer to the resist threshold. At higher energies, the line edge roughness improves considerably. That means that we've controlled 2 out of our 3 factors. But that last factor, the feature size, we need to account for that one too. The good news is that there is an easy way to adjust for the feature size being too large. Just need to bias the feature size down. This is sometimes called overdose and undersize. Offset from our target size is known as the process blur for the given resist and exposure conditions that we're using. We can bias down the exposed area to account for that process blur and get the actual feature size we're aiming for. So now we've managed to figure out dose that will work well for one resist with one set of exposure conditions on one particular film stack. But in order to make your device, you need multiple layers with different patterns and different films. Are you really supposed to do this calibration for every single one of them? To answer that question, let's step back and look at what factors impact resist sensitivity. The visual I use for this is a pyramid, and like the pyramid builders of yore, you need a solid foundation. EBL, that foundation is your resist composition. If you change your resist, you're building a new pyramid. The next layer is development conditions, developer concentration, temperature, time. The next layer up is accelerating voltage, and at the top is pattern density and material effects. So we're going to start at the bottom and work our way up. There are 4 families of EBL resists. You may find that one resist will work for all of your processing, or you may need to use different resists for different processing steps. The best thing to do is to find and use the right resist for your application. But wait, didn't I just make the point that if you change your resist, you're changing the foundation of your process? Yes, and that is true. If you change your resist, you have a completely different process. It is also true that not all resists work for all processes. Please don't try to use a resist that is ill-suited for your application just because you are familiar with it. PMMA, or polymethyl methacrylate, is the oldest EBL resist type. MMA, which is the monomer version of PMMA, is used in combination with PMMA for many liftoff processes. HARP is also a member of this family, just manufactured by a different company. PMMA processes are incredibly stable. Once you find parameters that work, it will work for years. The main issue with PMMA is its etch selectivity is fairly low. It is therefore primarily used for liftoff processes. The next family of EBL resists addresses this shortcoming of PMMA. CESAR and ZEP are similar products, again from different vendors, with much improved etch selectivity. The main downside of these products is that they are more expensive than PMMA. They can be used with PMMA for liftoff processes or as a single layer for etch applications. While the PMMA and CESAR ZEP families are positive resists, the next two families of products are negative resists. The areas that you expose remain, and all unexposed areas are washed away during development. This can be critical for certain designs. HSQ and HSiQ are the shorthand names for hydrogen silsesquioxene. HSQ is very expensive. It has a very short shelf life unless stored properly, and some of the developers used with this material are extremely hazardous to your health. On the other hand, HSQ is the resist that has produced the world record minimum feature size. It has extremely good lineage roughness, making it ideal for optical applications. And because it essentially becomes silicon dioxide upon exposure to the E-beam, it has very good etch selectivity to chlorine etches. I will mention one more family of resists, the MAN and ARN family of resists. These are negative resists, which are sensitive to both UV light and electrons, which can allow for some clever hybrid processes. At the time of recording, I have not worked with these resists personally, but wanted to include them in this overview for completeness. As you consider which resist to use, keep in mind that you should use the right resist for the application. If HSQ is the right resist to use it. If PMMA is the best choice, use it. Don't be afraid to use a different resist for a different step in your process, if that is the best choice for that step. There will be some extra work in the beginning to determine the best parameters for that resist, but this will ultimately make your research life much easier in the long run. The next layer in our pyramid is development conditions. In photolithography, we have a standard developer that we use for nearly every resist. This is not the case in electron beam lithography. If you are working with PMMA, you can choose to use different concentrations of MIBK IPA, or IPA water, or even methanol water. PMMA, CESAR, and ZEP can all be developed at room temperature, or they can be developed cold. HSQ can be developed in different concentrations of TEMA, or you can use a salty developer. The point here is that you have options. Why would you choose one developer condition versus another? Well, sensitivity is one reason. Let's look at PMMA. If you choose to use MIBK IPA as your developer, you will need 3 to 4 times the energy to expose that resist than if you use IPA water as your developer. HSQ has similar issues depending on which concentration of TMA you are choosing to work with. The benefit of using a developer that requires a low dose is faster throughput. The benefit of using a developer that requires a higher dose is that you get better contrast between the exposed areas and the unexposed areas. As we saw with choosing the resist, there isn't a one-size-fits-all solution here. Similarly, when it comes to cold development, there is an advantage to working with cold developers. You can achieve smaller features with less process blur if you develop cold. So why doesn't everyone always develop cold? Well, cold development is very sensitive to the temperature of the developer, which makes it easy for there to be a process shift. Room temperature development doesn't have that problem. So if you don't need cold development, you probably want to skip it. Now we can talk about accelerating voltage. There is a good paper from Acteri et al. That simulated electron behavior at different accelerating voltages. They saw that the dose to clear increased linearly with increasing voltage, a result that agrees with what folks find experimentally. At the risk of oversimplifying things, the reason for this is that as the accelerating voltage of the electrons goes up, the likelihood of any given electron interacting with a resist molecule goes down. So you need more electrons overall to break or cross-link the polymer chains at higher voltages. Since NanoLab has two EBL tools, one at 50 kilovolts and one at 100 kilovolts, if you know the dose at 50 kV, then you should expect the dose for the 100 kV tool to be about twice as high. A factor of 2 difference is a huge change in dose, which is why accelerating voltage is the third step of our pyramid. However, the good news is that accelerating voltage is a parameter that you set and forget. We don't typically vary the accelerating voltage on the tools, so most folks pick one tool, characterize their process on that tool, and move on to other challenges. The final step of our pyramid is material effects, which includes proximity effect correction. The proximity effect is a consequence of how electrons interact with matter. When an electron encounters the resist, there's only a possibility that the electron will interact with the resist. If the electron passes through the resist, it will then enter the underlying film and/or substrate. At some point, that electron will interact with an atom and scatter. When it scatters, that electron may pass back through the resist as a backscattered electron. For a perfectly uniform pattern, this wouldn't be a problem. However, patterns are never perfectly uniform. They all have a finite size, and often the pattern density varies by quite a bit. To understand the proximity effect, we're going to return to our resist energy profiles from earlier, except that this time we need to include the backscattering component of the electrons. This was left out earlier. When you sum the different contributions, you get a curve that looks like this. The feature at the center is getting more energy than the features at the edges. Let's look at a real-life example. Here, we have a large photonic structure made up of thousands of smaller circles. The circles in the center are oversized compared with the circles at the edge of the device. So now you know what the proximity effect is, and you know why you might need to account for it. Now what? Well, to start with, we need a true model of the electron scattering behavior. Here at UC Berkeley, we use the Monte Carlo simulation software Tracer from Genesis, which interfaces very nicely with the Beamer software that we use for proximity effect correction. In Tracer, you will model your resist, film, and substrate stack to determine the Gaussian coefficients for your materials. The graph we see here is very similar to the energy profiles we've been looking at throughout this presentation. The notable differences are that now we're graphing the energy input radially instead of as a feature, and that the x-axis is using a log scale, not a linear scale. The energy distribution can be modeled by two Gaussians, one for the short-range correction and one for the long-range correction. These have characteristic length alpha and beta respectively. By default, the short-range correction is often Beamer, and in this presentation, we will only consider the long-range correction. So let's run a naive proximity effect correction on that photonic structure from before. I want to pause for one moment just to say that there are a lot of nuances and subtleties when doing these corrections. Every new member who is getting on a Crestec tool is invited to meet with me for a data prep session to go over your specific pattern before qualifying on the tool. You can also reach out at any time to have another review session, particularly if you are struggling with your design. But for the purposes of this talk, let's just run with the default Beamer parameters. When we do that, we get this result. The different colors correspond to different dose factors. A dose factor is the multiplication factor that is needed to uniformly expose each portion of the pattern, and we'll talk more about dose factors in a moment. But I just wanted to give you the satisfaction of seeing that when we run with proximity effect correction, we do in fact get the desired result. Here we see the difference in size between the features in the center of this array and the features at the outer edge is 3 nanometers, which is within the design tolerance. Let's slow down for a moment and discuss the beta number in greater detail. When we are modeling the proximity effect correction, we start with a Monte Carlo simulation of the electrons incident on the resist, the film stack, and the substrate. Imagine a pen pointed down at the sample. You are simulating electrons coming off that pen and modeling the energy density of electrons radiating from that singular source. The x-axis is the radial distance from the source in microns, and the y-axis is the energy density. These individual curves are all referred to as point spread functions, or PSFs. In this graph, we have multiple PSFs for different substrates and resist combinations. For each PSF, we can then fit a Gaussian to determine the beta for each material stack, which are listed in the table. The beta value is an indication of how far away from the point source you must be to be isolated from that point source. By the way, there is a great application note from Genesis Online. The link is shown here. It's a 3-page PDF that walks you through how to simulate different material stacks. If you know your dose for a particular film or substrate stack, you can use this comparison to estimate the required dose for a new film or substrate stack. I strongly recommend that you run these models when working with new materials. Back to beta. Let's take a look at a pattern converted with 2 different beta values. In this case, instead of changing the substrate, I've changed the accelerating voltage. This gives a different beta value. ZEP on silicon at 100 kV has a beta of 29.3 microns, whereas ZEP on silicon at 50 kV has a beta value of only 9 microns. Here we have the same pattern, and we can compare the dose factor for these 2 different PSFs. I've modified the default color scale so that the colors are the same for both simulations. You can see that the actual dose factors are quite different. At 100 kV, the dose factors are all 1.43 to 1.60. At 50 kV, the dose factors range from 1.28 to 1.51. You can also see that in this example, the individual shapes that make up the pattern are much smaller for the simulation with the smaller beta. To understand this, let's see this design in the context of the different beta values. I've drawn 2 circles, one with a radius of 9 microns and the other with a radius of 29.3 microns, centered on the A of the Cal logo. You can see how the design takes up considerably more of the 9 micron circle than the 29.3 micron circle. This is why we need such higher dose factors for the 100 kV run. This also helps explain why the 50 kV version has smaller shapes at the edge of the logo. For a beta of 9 microns, this design fills a larger proportion of the circle, so the features near the edges will have more dose variation. Consequently, the shapes need to be smaller to account for that variation. I want to pause here and emphasize something. I do not want you to think that there is a benefit for choosing 100 kV because the beta is larger. Nor do I want you to think that there is a downside for choosing 100 kV because the beta is larger. That is not the point of these examples. The point of walking through these examples is to truly understand how the proximity effect works so that you can make process choices to get the pattern that you want in the end. So now that we've walked through a few examples, let's put this all together for a final example pattern. I call this a tower calibration pattern. This pattern can really help you find a robust process for your EBL resist. This pattern is made up of 4 different grading structures with different fill percentages. The 0% fill is just a single line. The 25 and 50% fill patterns have gradings of that fill percentage composing the entire square. And the 100% fill pattern has a single line surrounded by 2 large rectangles on either side of it. What is key about this pattern is that the size of each grading square is 4 beta in width and length, and you will see why once we calculate the proximity effect correction. The familiar rainbow colors represent the different PEC dose factors, with red being a dose factor of 1.58 and blue being a dose factor of 0.72. What you see is that the patterns with a higher percentage of fill have a lower dose factor, and the patterns with a lower fill have a higher dose factor. An important number for you to recall is that a dose factor of 1.0 is defined to be at the center of a grading with 50%. that has a dimension of 4 beta. When you run the PEC model, you can look at the resulting dose factors to understand what type of density you are working with. If your patterns have a small total area, you may only have a few dose factors up near 1.5. In that case, you have a very low density pattern. Personally, I find it helpful to have these reference points when analyzing a PEC result. What makes the tower calibration truly powerful is that you can use this pattern to determine the optimal dose for your process. You don't have to use your real pattern to determine dose. Here's what you need to do. Create a point spread function for your resist stack and substrate. You will need to find your beta value for your materials at this time. Create the squares of the appropriate size. I have code to do this for you for a given beta. Import that pattern into Beamer. Run a proximity effect correction using the point spread function you found earlier. Now you need to set up a dose array for whatever range of doses you want to test. Export and run this job on the tool. Here's what that looks like in practice. We have an SEM image with 7 different tower patterns in it. The lowest dose is on the left and the highest dose is on the right. The best dose is the tower pattern that works for all densities. Because you have tested the process at multiple densities, you know that the dose that you find using this method will work no matter what your pattern ultimately looks like. Do you have to use this method to determine your dose? No. You can test your process using your own pattern, but this is a more robust method for determining the optimal dose. This is the end of the first video for EBL class. In the next video, we're going to dive into some of the specific hardware needs for the Crestec tools here at NanoLab.